Section 9.1, Systems of Linear Equations, Solutions by Graphing. The objectives: determine whether a given ordered pair is a solution to a specified system of linear equations. Solve systems of linear equations by graphing. Example 1, checking solutions to systems. Show that 2, 1 is a solution to the system x minus 2y equals 0, 3x plus y equals 7. Our solution will be to substitute x equals 2 and y equals 1 into both equations. In the first equation, 2 minus 2 times 1, does that equal 0? 2 minus 2 equal 0, which is a true statement. In the second equation, 3 times 2 plus 1, does that equal 7? 6 plus 1 equals 7, so it's a true statement. Because 2, 1 satisfies both equations, 2, 1 is a solution to the system. Example 2, checking solutions to systems. Show that 0, 4 is not a solution to the system. Y equals negative x plus 4, y equals 2x plus 1. Substitute x equals 0 and y equals 4 into both equations. In the first equation, 4, does that equal negative 0 plus 4? 4 equals 0 plus 4, which is a true statement. In the second equation, 4, does that equal 2 times 0 plus 1? 4 equals 0 plus 1, which is a false statement. Because 0, 4 does not satisfy both equations, 0, 4 is not a solution to the system. To solve a system of linear equations by graphing, the procedure will be: step 1, graph both linear equations on the same set of axes. Step 2, observe the point of intersection, if there is one. A, if the slopes of the two lines are different, then the two lines intersect in one and only one point. The system has a single point as its solution. 2B, if the lines have the same slope and different y-intercepts, then the lines are parallel. The system has no solution. 2C, if the lines are the same line, then all the points on the line constitute the solution. There are an infinite number of solutions. Third step in the procedure, check the solution, if there is one, in both of the original equations. Consistent and inconsistent systems of linear equations. By definition, a system is consistent if it has one or more solutions, while a system is inconsistent if it has no solutions. We're going to walk through this example, number 3, solving systems. Solve the system of equations by graphing. Y equals negative x plus 4, y equals 2x plus 1. Those two equations are graphed on this coordinate plane. The blue line here is y equals negative x plus 4. The green line here is y equals 2x plus 1. And our solution is their point of intersection, which is indicated by the red dot, at 1, 3. So in example 2, we showed that 0, 4 was not a solution to this given system. However, by graphing both equations, we see that the two lines appear to intersect at the point 1, 3. We can check that 1, 3 satisfies both equations by substituting x equals 1 and y equals 3 into both equations. Our first equation, y equals 2x plus 1, and our second equation, y equals negative x plus 4. Plugging it in, on the left I have 3. Does that equal 2 times 1 plus 1? And on the right, 3. Does it equal negative 1 plus 4? Simplifying the math on both sides, we have 3 equals 3 on the left and 3 equals 3 on the right. Since both substitutions give true statements, the point 1,3 is the solution to the system, and the system is consistent. Solving systems of linear equations by graphing. Some things to note. Before working the examples in this section, you might want to review graphing lines in Chapter 10. Recall that lines can be graphed by plotting intercepts, finding a point on the line, and using the slope to find another point, or finding 2 points. Example 4, solving systems. Solve the system of equations by graphing. Y equals negative x plus 4, x plus y equals 2. The line in blue here is y equals negative x plus 4. That's our first line. The line in green here is x plus y equals 2, which is our second equation. And you'll notice that these two lines don't appear to have anything in common as far as points of intersection, because they appear to be parallel lines. So the graphs of the lines of the equations in the system are shown to the right. The lines are parallel. This can be shown by writing the equations in slope-intercept form and noting that they have the same slope and different y-intercepts. The first equation, y equals negative x plus 4, has a slope m of negative 1 and a y-intercept of 4. The second equation, y equals negative x plus 2, has a slope m of negative 1 and a y-intercept of 2. Since the lines are parallel and do not intersect, and there is no solution to the system is inconsistent. Consistent and inconsistent systems of linear equations. By definition, if the graphs of two linear equations are the same line, then the equations are dependent. If the graphs of two linear equations are different lines, then the equations are independent. So if they're the same line, it's dependent. Different lines, independent. Example 5, solving systems. Solve the system of equations by graphing y equals negative x plus 4, 2x plus 2y equals 8. In this situation, both equations are graphed and they end up being exactly the same line. There's just one line because both equations represent the same line. That is, they coincide. Any point that satisfies one of the equations will also satisfy the other. The system has an infinite number of solutions, and the equations are dependent. Putting both equations in the slope-intercept form shows that they are identical. Solving 2y plus 2x equals 8 for y gives the following. First, we subtract 2x from both sides, giving us 2y equals negative 2x plus 8. Then we divide everything by 2, which gives us y equals negative x plus 4. This is the same as the first equation, which was y equals negative x plus 4. Since y equals negative x plus 4 for all points on the line, we can write the set of all solutions in the form x, comma, negative x plus 4. Our order pairs typically are x, y, and that is really what we have written here when we have x and negative x plus 4, because negative x plus 4 is what we've said that y is equal to. Solving systems of linear equations by graphing. It's important that you understand to use the graphing method, you have to graph the lines as accurately as you can. And then you need to be sure to check your solutions by substituting it back into both of the original equations. Of course, if you have fractional estimates, we may not check exactly.